Greetings once again, everyone. This is Jeff Wilkerson, Professor of Physics at Luther College. Yesterday, we did a quick calculation. This was for the benefit. This was a practice calculation for the benefit of the students who are currently taking Engineering Science and Physics 150 here at Luther College. And we looked at how to scale densities, how to look at densities to get a real quick estimate of what the density was of one star compared to another. And we decided that Vega in the upper main sequence. We look at main sequence stars that were fusing hydrogen into helium in their cores, and we decided that Vega in the upper main sequence was about 9 times more dense than Tau Ceti in the lower main sequence. Now, we should point out that is an average density. We didn't talk about that, I don't think, yesterday, to say stars are very dense in the core. They have a high density gradient, so they're very dense in the core relative to the surface. So this is the average over the entirety of the star. And remember that we looked at, we made the assumption that they were spherical, these stars. So we said the volume was 4/3 pi r cubed. Now, I thought after this morning I woke up and I thought, well, why not ask the question about a red giant star? So let's do that. And to say when a star has ceased fusing hydrogen into helium in its core, there's no more hydrogen there, it will start fusing hydrogen into helium in a thin shell around that core. And at that time, when most of its power generation is coming from hydrogen fusion in a thin shell around an inert helium core, that's what we call a red giant. So that star has become a red giant. What it does is a red giant. It's got a hot core and a cool surface, and the reason the surface is cool is because it's pushed, the pressure has pushed that outer layer out. So it's a giant star because the star gets very big, and it's got this low density envelope. It's got this very large radius. The outer layers of the star have become ballooned out. And so now the gradient, the density gradient is going to be pretty severe, but we're going to ignore that again. We're just going to say, what's the average density of a red giant star compared to these other stars that we looked at yesterday? And so let's compare Vega. Let's figure out how many times more dense Vega is than Aldebaran, the eye of the bull. That's our Arabic word that translates as eye of the bull in Taurus. And so we've got Aldebaran is about 1.2 times the mass of the sun and 45 times the radius of the sun. So you see the big radius. You know, it'll keep getting bigger. So there are supergiant stars that are bigger than this. But we can talk about that another time. So what we're looking at here right now, let's say the density of Aldebaran divided by the density of Vega is going to be 4/3 pi times the radius. Let's do the mass first. I'm going to put the mass on top. I don't know why I was doing the volume first. But the mass of Aldebaran divided by 4/3 pi, the radius of Aldebaran cubed, divided by, we did all this yesterday, go back and watch that video, we did it for the 2 main sequence stars. The mass of Vega divided by 4/3 pi, the radius of Vega cubed. And what we did yesterday, all the constants are going to cancel out. They're the same on the top and on the bottom, so we cancel out all the constants. And then we've got the mass of Aldebaran divided by the mass of Vega times, why that says squared, I don't know. Multiply the top and bottom by the radius of Vega cubed to cancel it out in the bottom and bring it up top. So it's going to be the radius of Vega cubed. He says cubed and he writes squared again. You can tell it's the end of the week, right, folks? Radius of Vega cubed divided by the radius of Aldebaran cubed. So I've been a little bit off all this week making these kinds of mistakes, but here you go. So anyway, this is what we got. This looks like 1.2 solar masses divided by 2.1 solar masses. So 1.2 solar masses divided by 2.1 times the radius of Vega cubed, which is 2.3 solar radii, over the radius of Aldebaran, which is about 45 solar radii, that whole thing cubed. The units cancel out. We've been practicing that in our class too, thinking about carrying these units through and doing analysis of the units. The dimensions cancel out because this is a ratio. So we're saying how many times more dense is one star than the other star. So let's plug in our numbers again, and we got 1.2 over 2.1 is going to give us 0.57, excuse me. So this is 0.57. We'll keep an extra digit in there like we like to do in the middle of a calculation. 2.3 divided by 45 cubed is going to be 1.335 times 10 to the minus 4. So that's going to be 0.000135. I'll keep an extra digit there. So you see that radius cubed, that's so much bigger. Aldebaran is so much bigger than Vega that the radius cubed really makes this balloon. It's going to bring the density way down. And so this is going to give us 0.571 times the 1.335 times 10 to the minus 4 is equal, I messed that up. I don't use a calculator very often. 0.000133 is equal to, let's try that again. We know that's not right. As I said, I don't use a calculator all the time. 0.00076. So I had intended to do the density of Vega over the density of Aldebaran. That's what I said I was going to do when we started, but again, I just started this way. So Aldebaran is what is that? That's a percent. That's a thousandth of a percent as dense. Let's take the inverse of that and do see what it is. It says that Vega is going to be about 13,000 times more dense than Aldebaran. And it's all because of that radius being cubed. So you see how these giant stars can be on the order of 10,000 times less dense than these low-density, high-mass stars. Remember that Tau Ceti was a factor of 9 more dense than Vega, and so that would be another factor of 10 in here. So instead of 10,000, 100,000 times less dense. Why? Because we got stars that are about the masses of these other stars. Really, the mass hasn't changed very much. The mass played very little role in this calculation. The mass hasn't changed very much, but the radius got 20 times bigger. And you take 20 and you cube it. What is 20 when you cube it? 20 times 20 times 20 tells us, oh, look at that, it's 8,000. That's our factor of about 10,000 difference that we got right there. So this is what we're looking at here to say, this was a higher mass star, so we even had less mass over here. So that's where that difference comes from, somewhere on the order of 10,000 times less dense for these red giant stars. So these red giant stars are really big puffy things on average compared to the upper main sequence stars, and the upper main sequence stars are really low density compared to the lower main sequence stars. So that's what we got for you. Another calculation, another sample calculation in case the 150 students want to be watching this and do another practice density scaling calculation. But another thing to think about, interesting how red giant stars are so much less dense than main sequence stars. Okay, thanks for watching, everybody. Have a great day.